So let's look a little bit at the registration statistics of the Scottish Deerhound. And when I stole, no, I didn't steal. When I awarded all of your pictures off the internet, I do hope that that no wolfhounds snuck in. Okay, I'm pretty sure they're all deerhounds, but I did not spend all of the time these past months working on this seminar to figure out all of the fine nuances between the wolfhound and the deerhound. So hopefully these are all deerhounds. Okay, AKC population growth at the bottom, 1985, and then we go up every 5 years until 2010, and then every year from 2010 to 2018, which was last year, which is the last full year of registrations. And here's the AKC rank in order for the breeds. And you see that, and it's not that you have dropped precipitously in your ranking, it's just that so many other breeds get added over those 40 to 50 years that we're looking at here, and the majority of those breeds that did get added have more numbers in population than the deerhound, so your ranking just keeps on going down. So number of dogs, individual dogs registered, 196 in 1985, 157, 79, 158, almost 200, and then we drop down. So certainly the numbers have dropped, and those numbers especially start dropping in the early 2000s, as I said, when we had economic things going on, 2007, 2009 recession, and so forth. We got down to 60 deerhounds AKC registered in 2013. We jumped up to over 100 in 2014, and then down and up. You've got this bimodal thing. Every other year you go up, down. So you're around between 80 and 100 dogs registered per year. All right, there are certainly breeds that have a lot less dogs registered each year. So while you're a small breed, you are breeding and you do have numbers. Some breeds have some genetic diseases, and they have numbers even smaller than yours in terms of how many dogs are being bred, and they're afraid to breed. They've got a really bad problem with epilepsy or some other disease, and they know of an epileptic dog in just about every single family, and they're just frozen in fear that they're going to produce another epileptic dog, and they don't breed, and they've stopped breeding. That's the kiss of death of your breed. You know, your breed's not going to die from epilepsy. Your breed is going to die from attrition because no one's breeding. Your gene pool goes down, your choices go down. You no longer have choices as to who to breed to because there are only a handful that are available, and so that is the worst thing that can happen. Here are the number of litters that have been produced, and certainly this shows us that the number of litters has gone down over 50 years, and this follows the same trends that we said before. Now, so number of litters does have to do. Well, number of litters could also be, missed litters if there's problems with fertility, that maybe we're having inbreeding depression going on, and that those are issues that we deal with. The number of puppies born in a litter and registered, could be going down. But if we take the number of AKC dogs registered each year by the number of litters that were produced that year and divide them to say how many puppies per litter were registered, and we all understand that does not mean how many puppies were born, okay? Because not everybody in a litter gets registered, right? And sometimes you get more blue slips than puppies that survive even the first week or two of life, and so forth. But you got to figure whatever forces are taking puppies out that don't get registered, or that are pet dogs that don't get registered, they'll be fairly even so that we can compare year to year. And so when you look at puppies per litter from 1985 up to 2018, what we see is that, yes, there's individual variation, as we would expect with any type of population that you're surveying, but in actuality, when you apply statistics to this, the number of puppies per litter has not changed in 50 years. So if someone's saying that our breed is going down a rabbit hole of inbreeding depression and we are going to lose our breed because of it, the number one thing you would see is decreased litter size and decreased fertility, and based on the numbers, we are not seeing that. And the vast majority of all breeds, we are not seeing that. And so the big cry about genetic diversity, and we're losing diversity, and we're increasing our homozygosity, is really just a big cry. It has nothing to do with the health of your breed or what you're supposed to be doing when you breed your dogs. And we'll get into some more about that. So the next part of my talk follows an article that I wrote a really long time ago, in the 90s, called The Ins and Outs of Pedigree Analysis, Genetic Diversity, and Genetic Disease Control. And if you just Google ins and outs of pedigree, it was the most frequently reprinted article that I wrote from the 1990s, and you can find it anywhere. Serious Dogs has a copy of it there, and I have a truncated copy of it in the handout for you to look at. But we're going to go through what was in that article tonight, but utilizing the pedigrees of Scottish Deerhounds and your pedigrees. And so I want to take a moment to thank the people that donated their or shared their Scottish Deerhound pedigree database so that I could do this analysis. And I'm sorry, their names are Mick and Lennis Peach from the UK. So they have a complete pedigree database in the UK that goes all the way back to the founding ancestors of the breed. And that's very helpful for us to understand about the background of your breed. The AKC also gave me the entire Scottish Deerhound electronic computerized database so that I could merge it with the UK database, because their database does not go back to founders. Unfortunately, when the AKC in 1980 migrated from their mainframe to their present computer system, the migration was going to be very, very difficult, and they did not migrate everybody. They just migrated who was behind the pedigrees that were coming in at that point. So there are dogs from the 70s, handfuls of dogs from the 70s or 80s that are in the AKC computerized database, but pretty much it's 2000 and on where every single dog registered at AKC is listed. So we have complete records on 18 years of breeding, but they do match up to the UK dogs, and it was very helpful for the analysis. Okay, so my next question is, my last mating was N, or if you didn't have a last mating, I prefer to do, and your choices are inbreeding, line breeding, outbreeding, outcrossing, or crossbreeding. And so if you are on the webpage, polev.com/deerhound, this question came up, you just tap your answer. If you are texting, you're just texting A, B, C, D, or E. If you're asking me what is the definition of one of those, I am sorry, that is the point of this question. Okay, do you understand what you're doing with your matings when you say you're doing these things? And we will define them after you answer this question. Okay? So we've got 10 results so far. Am I staying close enough to the microphone? People in the back, can you hear me? Okay. Okay, we've got 16 people. Let's get a couple more. Oh, somebody backed themselves out, 16. And when you log on, if you're on a web page and it says if you want to register, you don't register. All of this is anonymous. Even if you did register, all this is anonymous, because I'm going to ask you some really personal questions as we move along. So you don't have to worry about putting your true answers in there, because no one is going to know that it was you that put that answer. Okay, so let's see what our answers are. So 37% say you do outcrossing, 32% say you do outbreeding, and 32% say you do line breeding. Okay, let's define these. Inbreeding to a breeder, I understand, is father-daughter, full brother, full sister. That is an inbreeding. Okay? To a geneticist, and if there is a common ancestor in both the sire and the dam's side of the pedigree, so a dog that appears in the sire's pedigree and the dam's pedigree, there is a calculable number in terms of the relationship between the sire and the dam, and that is the inbreeding coefficient. I'll define that further for you in a second. So that is what inbreeding is to a geneticist. Line breeding is what most of you think of when you are doing a close mating, where you are trying to concentrate the genes of particular dogs and reproduce them in offspring. And in order to determine what a line breeding is, you need to know what the average inbreeding coefficient is of the population. We'll define and talk about that in a second. So if the average relationship between a sire and a dam in any mating in a breed is 17%, let's say, then a mating that has a number higher than 17% is an outbreeding, is a line breeding. a number less than 17%, where the parents are, the sire and dam are less related than the average of the breed, that would be considered an outbreeding. All right? And so that's where many of you put outbreeding. Now, I also do understand that as breeders, you're fixed on a term called outcrossing when you mean outbreeding. All right? So all the people with outbreeding and outcrossing, we might as well add those together and say that 65% of the breed does outbreeding and 35% does line breeding, does closer breeding. We as geneticists like to reserve the name, the word cross, with when you're actually crossing two different breeds together. All right, and that's what a crossbreeding is. And so crossbreeding would be like, you know, and a long time ago, I used to say no one does crossbreeding, but then all the designer breeds came along, and so a lot of people were doing crossbreeding. But pretty much you're doing either line breeding or you're doing outbreeding based on the relationship of the parents. So inbreeding, breeding very closely related dogs. Line breeding, less intense form of inbreeding, concentrates the genes of a particular ancestor. Outbreeding, the dogs are less related than the average of the population. Crossbreeding between two different breeds. So here are three different populations of dogs. And there's a purebred dog. There is a designer bred dog with your original cockapoo there. And you've got your random bred dog. But when I look at this slide, I'm actually looking at two populations of dogs, okay? I'm looking at a purebred dog and a designer bred dog, where a human decided what two dogs were going to breed together, all right? So it's a purposefully bred litter. And the random bred dog, where a human had no input as to which dog bred to which dog. They just were left up to their own and did it on their own. So when I look at this, I see that as a random bred dog, I really can't do anything as a veterinarian to try to improve the genetic health of those dogs because humans are not involved. But in both purebred as well as designer bred or even bred for rescue or any kind of breeding where two dogs are brought together, where a person's doing it, there is a responsibility for some health checks and health conscious breeding. So here's one of my favorite cartoons, Get Fuzzy, and Rob says, ever hear the expression, familiarity breeds contempt? And Satchel sits there and thinks for a second, and he says, no, in the dog world we say familiarity breeds hip dysplasia. So this is what the public believes about dog breeding, is that all of the problems with dog breeding have to do with inbreeding and familiarity, that because we're breeding closely related dogs to each other, that makes them sick. It says so in the Bible, and that's where they're coming from. That's the and so that's something, and that's why the designer breeding. No one had to come out and say that designer bred dogs were going to be healthier. It was just assumed. It's like, of course, because they're a crossbreed, it's going to be healthier. And so the converse is, well, because it's purebred, it's going to be sickly, and that is where we have to educate the public. And so this is part of what we need to understand, is that how our breeds and our breeding is being perceived by the public and received by the public. So I do need to define two terms for you more specifically. One is that inbreeding coefficient. It's called the Wrights Coefficient. Sewell Wright coined it and came up with a calculation for it in the early 19-teens, like I think it was published 1917 or something like that. And so let me read the definition first, and then we'll go through it word by word. The proportion of all variable gene pairs that are likely to be homozygous due to inheritance from ancestors common to the sire and dam. So let's break this down. The proportion of all variable gene pairs. So what is a variable gene pair? Well, we know all genes come in pairs. You get one from the mother and one from the father, and they pair up together, and then how they relate to each other explains what you see in the offspring. So a variable gene pair has to vary within the breed. So if there are gene pairs that are not variable, that always have the exact same genes at that pair within the breed, then it's non-variable. So a gene pair that makes a dog is non-variable. A gene pair that makes a Scottish Deerhound a Scottish Deerhound is non-variable. That's why you breed 2 Scottish Deerhounds, and I bet no one in this room has ever produced a Chihuahua. Okay. So these are all non-variable gene pairs. So we're only looking at the gene pairs that vary when we are looking at that inbreeding coefficient number. They're likely to be homozygous. So homo means the same. Heterozygous, hetero means different. So homozygous means that the gene at that gene pair is the same that came from the sire and the dam. Now it might be a little a recessive gene. It could be a big A, a dominant gene. It could be an additive gene. It doesn't matter what type of gene it is, but it's the same variety of that gene at both places in that gene pair. And that they're the same because of inheritance from ancestors common to the sire and dam. So that little a could have come from the same dog through the sire's pedigree and the same dog through the dam's pedigree because of the relationship between the sire and the dam. So the proportion of all variable gene pairs due to common inheritance from the sire and dam, 17% inbreeding coefficient means that 17% of the variable gene pairs will be expected to be homozygous due to common ancestry. Another way of looking at the inbreeding coefficient would be to look at it only as it relates to a single gene pair. So what I just said was for all the gene pairs, we expect 17% to be homozygous. We can also say what's the chance of a single gene pair being homozygous. That would also be 17%. So that's what that inbreeding coefficient tells us. The one other term I want you to understand is a relationship coefficient. So the relationship coefficient is a measurement of the probable genetic likeness between an individual and a particular ancestor. So if you say I am line breeding on Super Charles, who was an ancestor that occurs in both the sire and dam side of the pedigree, the relationship coefficient tells you what percentage of genes you would expect the dog in the pedigree whose mating you're looking at would inherit from Super Charles off both sides of the pedigree. It's the percentage of genes that individual ancestors have in common from descent. And there is a complicated formula for the relationship coefficient because it also takes into account the inbreeding coefficient of the pedigree you're looking at and the inbreeding coefficient of the ancestor you're line breeding on, so it becomes complicated. But it's really easy to approximate the relationship coefficient with what's called a percent blood calculation. And all that is that it takes the position of that dog in the pedigree and you get a certain percentage of genes from that position. So each parent contributes 50% of the genes. Each grandparent contributes 25% of the genes. Each great-grandparent contributes 12.5% of the genes. So if you have a dog that's a grandparent on one side and a great-grandparent on the other side, then you would expect the percent blood or relationship to be 50% plus 25%, 25% plus 12.5, or 37.5%. So you expect a third of the genes in the dog whose pedigree you're looking at to be from that dog that you're line breeding on. Okay, so you're not going to be able to all read the numbers on this. Maybe we can zoom in on the video and you can look at it at home when you get the videos, but I'm just going to walk you through this a little bit. So this is an analysis of the entire combined AKC and UK stud book going all the way back. It's only going back to the year 1900 for many reasons, but for one reason is that computer language, when they date things, when they wrote the original IBM computer languages, they decided that nothing really happened prior to 1900. So actually, when you analyze these computerized databases, your 1800 dogs tend to fall out. Not that they fall out, the relationships are there, but they're not. But their birthdays are not being recorded. So we're going for every decade from 1900 to the present. And what we see here is the mean number of generations behind those dogs. So the Scottish Deerhounds from the decade of the 1900s had on average 17.1 generations of dogs behind them. So it's got, this database that we use was an excellent database that went all the way back to founders, okay? So 22 generations by the 1910s, and your dogs today have over 70 generations of purebred Scottish Deerhounds behind them. And so this is really where your breed was developed and where it came from. the mean number of unique ancestors in the pedigree, because there are going to be literally millions and hundreds of millions of positions if you're looking at 70 generations in that pedigree. But those positions are only filled by a finite number of actual dogs. So dogs way back when are going to appear everywhere in the 70th generation, because that's where the breed started. But the number of unique dogs in that pedigree is still only going to be a finite number. So 161 dogs in the 1900s, you'll see it goes down to 0 here. It's using calculations down here when I'm dealing with 70 generations and over 30,000 dogs. It takes a week at a time to calculate these, and I actually ran out of time on my computer. But it doesn't matter. The concept is that this number goes up as you create more dogs. And people say, well, you're only recapitulating what was in the founders, and therefore we really lack diversity. But the bottom line is, when you still have 2,000 different individuals that you're breeding on in the breed, you've expanded that gene pool, you've increased choices, and that's what you're supposed to do with a breed. All right, so if you're a small breed and you feel that you're more related than 2 Labradors would be, well, at one point in time, the Labradors were in the exact same position that the Scottish Deerhounds were in their numbers, all right? And they were healthy at that time, and they're healthy now. And so the bottom line is the size of the breed population has nothing to do with the health. It's what has been selected for and what's being produced. So if you're producing a healthy breed, it doesn't matter whether you're a small breed or a large population breed, it's that you're doing health-based breeding and producing healthy dogs. So your inbreeding coefficient, let's take your all-generation inbreeding coefficient. So calculating that inbreeding coefficient going back to founders through the generations, what we find is that there was a 7% inbreeding coefficient in the decade 1900s. Certainly some of those dogs were related to each other as well, but if you don't have relationships beyond what is in the database, everyone is counted as a founder that doesn't have parents, and so they're not related to each other, even though they might be. And so what you see over time is that inbreeding coefficient, based on all generations, goes up, because if you have a closed stud book, the relationship of the dogs is going to get deeper and deeper, and that is going to slowly rise. And the object is for it to slowly rise. But when you're looking at all generations, it cannot go down. If you see it go down in a generation, that means that pedigrees from the 1950s were added to that computerized database that were not all connected back to their ancestors. So that you have truncated pedigrees where the dog in the 5th generation, their parents were not in the database, and so now all of a sudden that dog is counted as a new founder, and therefore that coefficient goes down. But we know if you have complete pedigrees, the number cannot go down. So based on all generations, your inbreeding coefficient is 18.8% for this decade. If you look at only 10 generations of pedigrees, those numbers continue to go up, but now we're truncating that calculation based only on the last 10 generations. So if dogs in the prior generation and the 11th generation were related to each other, they fall off the back of that 10 generation pedigree and are not counted. So you're looking at a finite 10 generations, the most recent 10 generations, what is the inbreeding coefficient? And that's very helpful because it allows us to compare one generation to the next and say, are we getting tighter? Are we expanding our breed choices so that the average mating is less related than the last generation, and that number goes down based on 10 generations? And that is a healthy breed pool when that number goes down. And so as you can see here, it went up during the formation of the breed, and then it started going down. It went up a little bit in the 80s and the 90s, so there were some popular Sire effects going on in the 80s and 90s. It definitely tells me that when those numbers went up, and then they started going down again in the 2000s and the 2010s here. So that's how you do that. If you look at just 5 generations, now it's only including the last 5 generations, which means tight line breeding. Individuals that are related to each other on the sire and the dam side only within 5 generations, and so those numbers will be smaller. But actually, in that regard, these numbers precipitously go down, and that's telling me that you guys avoid any line breeding in the first 5 generations as a breed. And that's something different than a lot of other breeds do. So it's obvious that you're using a concentrated effort to not breed closely related dogs to each other, and that's fine if that's what you're doing and it's for a purpose. But the bottom line is breeding for a lower inbreeding coefficient is not a goal in breeding. It has to happen for a reason, for something you're selecting for or against. And if we have an expanding population, then these numbers will naturally come down in a 10-generation pedigree just based on that expanding population. It's not something that needs to be artificially controlled. So here is a graph of the all generation, 10 generation, 5 generation, and as you can see, you get the formation of the breed here and adding individuals, and then it grows up here. This little dip is going to be due to dogs being added that did not have complete generations, because that's all generation. And here's your 10, and here's your 5 generation for the last 20 years. So you guys are not doing tight breedings for the last 20 years. And so if people are saying, well, it's because of rising inbreeding coefficients, that's not what's happening in your breed right now. This is just the AKC portion of the database that I received from the AKC. So it doesn't go back much more than the, I'm sorry, did I say it went back to 2000? The AKC pedigrees go back to 1980. That's when they migrated from the mainframe, not 2000. Okay, you feel a little better about that? So it's 1980s, the complete litter registrations are in the database, and then dogs from the 70s and 60s were added in manually when dogs came in that needed those dogs filled in off the mainframe. So, but just using that, we still see the same thing going on. We see it increased a little bit, and then in the 80s and further, it went down. You see the same thing there. Even though things go up, we do see in the 2000s and 2010s those numbers going down. That likely has to do with imports, with dogs coming from the UK or from other countries, because the AKC, if they add a pedigree and it has individuals that are already AKC registered, they would go back further, and this all generation number would not be able to go down. Okay, so if we compare that number, actually compare the number from the 1990s, because that's where I've looked at most of the breeds. Their 10 generation inbreeding coefficient of 14.8 for Deerhounds, and you look at all the other breeds here around that time period. You look at Briards at 15%, Bouviers at 13%. You look at Peers. You look at miniature poodles and standard poodles. You look at Rhodesian Ridgebacks and Siberian Huskies. These are breeds that all have very similar breeding coefficients as the Scottish Deerhound. You look at some breeds like the Nova Scotia Duck-Tailed Retriever or Norfolk Terrier, where their 10 generation coefficient is in the high 20s. It doesn't make them an unhealthier breed, but they are a much more tightly bred breed, and so there's still need to expand that population. You look at a Bichon Frise that has a very large population, and their numbers are at 19.5. The reason for that is it was a very strong popular sire effect, where a popular sire came along, everybody went to him, he produced a son that became a popular sire, everybody bred to him, he produced a sire, became a son that became a popular sire, everyone bred to him, and the entire breed truncates on a single popular sire line. The worst thing that could possibly happen to a breed, a very strong popular sire effect. And so, here you can see that. Short hair is very outbred breed, a very populous breed and outbred breed. Samoyed is very outbred breed in its development and existence. Borzoi is the same thing. Bernese Mountain Dogs. Everyone says Bernese Mountain Dogs are so inbred, they're dying. They've got this, this cancer that they're dying from. They're inbred. It's horrible. They are one of the most outbred breeds in the world. Okay. But they have an inherited cancer that kills a lot of dogs. And of course, because disease equals inbreeding, everyone says, well, it's because they're inbred. All right, but it's not. It's not. It's an outbred breed. And so these numbers and these terms really have nothing to do with the health of the breed. Let's look at the influential Scottish Deerhound ancestors in your breed. Maybe you'll recognize some names, maybe you won't. I'm going to go a little bit faster because we did start a little bit behind, and I want to keep this because I know you have a big specialty and a big day tomorrow. I don't want to keep you here late. So in the 1900s, St. Ronan's Ranger, who was born in 1901, on average, every Scottish Deerhound in the 1900s shared 10.9% of their genes with St. Ronan's Ranger, who was born in 1901. Okay, so he was a popular guy. He produced quality, and his kids were bred, and so everybody was closely related to him. So was Doran, I may mispronounce some of these, 9.8, Fingal 2, so would Houlihan or Houlihan, I'm not sure, and so forth down the line. So these are the dogs that were the most influential in the 1900s. In the, we're going by 20-year periods now. So 1900s through the 1910s. The 1920s through the 1930s, St. Ronan's Ranger, his influence actually went up, whereas Duran's influence went down, it cut in half. So what that's telling us is that Ranger's offspring produced quality that was propagated and even further propagated to increase his influence. And so with Duran did not produce the quality that people were looking for, or for whatever reason, and his influence went down in that regard. Some of these guys had influence and then disappeared and didn't really have significant influence after another 20 years, and so forth. And then new dogs in the 20s and the 30s came up. Tragic of Ross was born in 1923, and he contributed 12.9% to every single dog in the pedigree. So 12.5% is a great-grandparent. So he was as related as a great-grandparent to every single dog in those 20-year in that 20-year period. So he had a significant effect there, and you have other dogs contribute. You then go to the 40s and 50s, and we see that Ranger now drops down, but Duran actually picks up a little bit, and Tragic of Ross goes up. And then you've got new dogs from the 1940s, but also some from earlier years that are being bred on, and Timberwolf of Twinkling now contributes almost 20% to every individual in the breed and so forth. And we have 60s and 70s, and we see these numbers changing. Tragic of Ross went down slightly. We see Timberwolf of Twinkling went down precipitously in his input there. And then we have new dogs. We have Monarch of our Kingless at 18.2, Trajan of Rotherwood Carroll of Glengyle, and these might be dogs that now you may have even heard from starting to come out from the 1940s. In the 80s and 90s, we see that in the 80s and 90s, we see that Monarch of Art Kingless, his influence still remains strong. It went down a few points. Okay, we see in IGO of Art Class going from 2.5 to 8.1. So all of a sudden, his offspring and his descendants are becoming selected for and increasing his influence. We have Tragic of Ross remaining a strong influence, and we have these guys in the 80s and 90s, dogs from 1901 and earlier that still maintain a significant influence on the breed. And then lastly, this current decade, we have the same strong dogs being carried forth there. We have some new dogs. We have Kilbourne of Seamus from 1989 contributing 10.3% to the breed. So it's still 10 to 20 to 30 years later from when he was born, but his influence, those of his descendants, are influencing his contributions that are going up in that regard. And so this is how the changing influence of ancestors occurs in a breed based on what is being selected for and what is being selected against. You would expect that these dogs that continue to propagate and whose numbers continue to go up and be strong in breeds are because they are producing quality. Their offspring and their descendants are producing quality, and therefore they are continuing to be selected for breeding. And if they don't produce quality, then their descendants will not be selected for breeding, and their influence would go down. Okay. Influential AKC Scottish Deerhound ancestors. So again, only using the AKC database that went back to 1980. Okay, what we see is in 2000 to 2009, Gil Woods Paps, born in 69, 7.3%. Cranrocks Fenris O'Fernhill, 7.3%. Leith Ian of Dalmahoy, Gwen's Treefort O'Fernhill, and these are the numbers there and the years they were born. And then this, the 2010s through 2018, what we see is that these individuals stayed strong. Cranrocks Fenris O'Fernhill actually went down on average, looking at all AKC dogs, and you had some additional ones that jumped in there with those low numbers there. So you're recognizing dogs that you now know about, somewhat. Okay. So again, these are the influential dogs in your pedigrees. So that's looking at entire breed gene pools and what influences them. So we need to talk about how that influences what's happening in the matings going on in your dogs, in your breedings. So let's look at a pedigree here, and I selected some pedigrees based on the concepts that they show, and not necessarily because they're the most prolific dogs or the most popular dogs in your breed. So this is a Balnagown Devil May Care. He was born in 1990, it's a she, born in 1997. What is her call name? Anyone know her? Anyone hear of her? Okay. So she was born in 1997. When we look at a pedigree, the sire is on the top line, right here, and the dam is on the bottom line. The sire is on the line above him. His dam is on below. The dam is sire, the dam is dam, and so forth down there. And so I'll take out my colored flares and I'll start coloring in individuals who appear more than once in the pedigree. So does anyone appear more than once in the pedigree?
Yes.
Who?
Okay.
Cranrocks Fenris of Fernhill appears here in the pedigree as a great-grandsire, and here as a great-grandsire. So a great-grandsire, the sire to the paternal grandmother, and also the sire of the maternal grandfather. All right. What we also don't see on this pedigree is that he is the sire of Eclipse of Fernhill. So he appears 3 times on this pedigree right here. We also see Lionhill Highlands Haggis, who was also the sire of Lionhill of Balnagown Hoax, and also the sire of Lionhill Meg Marilis. And then we see Balnagown's Revenge as the dam that was bred to Haggis. And so therefore, Lionhill Balnagown Hoax and Balnagown Who's Foolin' Who, they have the same 2 parents. How are they related?
Siblings.
Okay, they are full, it's called full siblings. Could they be litter mates? Yes, they could, but they could also be a repeat breeding. But genetically, they are full siblings. So regardless of whether it's from the same litter or different litter, they are full siblings in that regard. And we also see Lionhill Meg Marilis being a full sibling to those 2 as well. So we have 3 full siblings in the 3rd and 4th generation of this pedigree. When you look at the 10-generation inbreeding coefficient, it is 26.9%. This is a very tightly line-bred pedigree. So because we're seeing all the common ancestry, when the average for your breed is 14 point something for 10 generations, when you look at all of the generations of the pedigree, it's 34.4%. Now when you look at a full brother, full sister, or a father-daughter mating in a pedigree, the inbreeding coefficient is 25%. We expect 25% of the genes to be homozygous due to inheritance from just that relationship. And this dog at 10 generations is 26%, and for all generations is 34%. Over a third of this dog's genes are homozygous due to common ancestry. Okay? So, and we'd say, well, we would never do, an inbreeding, a full brother, full sister, or father-daughter, but the bottom line is every single mating you're doing in your breed and every single other breed, if you calculate back to founders, is an inbreeding or a very tight line breeding, because of the common ancestors that founded the breed. So it has nothing to do with gee, how inbred is the breed, it's how old is the breed, and then a completely separate conversation of how healthy is the breed based on the detrimental genes that breed carries. So here is an arrow diagram. I won't go into it just for time's sake, but it shows the relationship that each of those 3 common ancestors had 3 descendants in that pedigree, and it carries down. And then this is the pedigree analysis, the 10-generation inbreeding coefficient. So the dog with the most influence in this pedigree is that Cranox Fenris of Fern Hill, who contributes 31.2% of the genes to devil-may-care. First appears in the third generation and appears 3 times, as we saw in that pedigree. The second most influential dog in this pedigree is Lion Hill's Angus of the Isles, who doesn't appear until the 5th generation, but he appears 26 times in the pedigree and therefore contributes more than a grandparent, starting from the 5th generation. We then see the other 2 dogs that were line bred on, Haggis and Revenge, who both contributed 25% because they appeared once as a grandparent and each appeared twice as a great-grandparent. So that was 12.5 plus 6.25 plus 6.25 equals 25. So they have the same relationship as a single grandparent, but they actually have more influence on the pedigree of devil-may-care because their genes can combine in devil-may-care from both sides of the pedigree and pair back up to influence each other. Whereas a grandparent's genes are always modified by the mates that it was bred to and then the mates that its offspring were bred to. So it's only coming down one side of the pedigree. So the relationship is the same, but their impact might be different. When you go down here to the 10th generation to find Tragic of Ross, and we know Tragic of Ross was born in 1923. So this is a dog that was born in 1997. And a dog that was born in 1923 doesn't appear until the 10th generation. So you take 0.5 and divide it 9 more times in half, and it'll give you 0.0000 something in terms of one time that they show up in the 10th generation. But you add up the 117,605 times that that dog appears in that pedigree, and he contributes more than a great-grandparent, even though he was born in 1923. So contributes more than a great-grandparent that you know of and that you knew that dog, you saw that dog in the ring. You didn't see Tragic of Ross. You need to look up and see what he's like because he influences everyone in the breed. Okay, next pedigree is Gil Woods Darwin. Does anyone know of this dog?
Yes.
All right, I found one, right? Okay. So Darwin is, what's his call name? Darwin. Made it easy, thank you. And then I go to these French breeds, you know, and I say, okay, and what was Darwin's call name? Georges Soja. Okay, we'll call him Darwin, okay? He was born in 2009. He's a male. And what we look at in his 3-generation pedigree here is that there are no common ancestors. In actuality, he is a very outbred dog. So his inbreeding coefficient is quite low. 10 generations is 3.9.
Lost your mic.
Hello?
Lost your mic.
Lost it entirely.
Maybe disconnected along the way. Stepped on something.
Nothing here. There we go. Okay. All right. So his 10 generation inbreeding coefficient is 3.9 compared to 14 point something is the average of the breed. And his all generation inbreeding coefficient is only 14%. Yeah. I think we need to tell them we need a new battery. Yeah, that's what it's going to be. It's just going on. Yes, I have to speak fast and in 18-second strips.
6-second strips.
Okay. So when we look at his, let's do that again. All right. I'm gonna speak louder until they get us a new microphone. When we look at his pedigree analysis, the most influential dog in his pedigree is Monarch. I'm probably mispronouncing that as well. Contributed 15.1% of the genes to Darwin. Monarch does not appear until the 11th generation of the pedigree and appears 36,341 times. Monarch was born in 1945. Okay, so contributes 15% to a dog that was born in 2009, starting in the 11th generation. Timberwolf of Twinkling in the 12th generation. I don't know if someone needs that for a new battery or something. Okay, and then Tragic of Ross, who we know is behind everyone oodles of times, over 1.5 million times, 1,626,000 times, starting in the 12th generation, still contributes more than a great-grandparent at 13.4. And if we want to work all the way down to St. Ronan's Ranger, what year was St. Ronan's Ranger born?
1901.
1901. First appears in the 14th generation, appears 158,508,405 times in Darwin's Pedigree. A dog that first appeared that was born in 1901 and contributes as much as a great-great-grandparent to Darwin. And so now we begin to understand about the background inbreeding in your breed. So I specifically picked the most outbred dog I could find that maybe you would know of, so that you can understand that when you don't have close line breeding, I mean, the common ancestry here, so these dogs first appeared in the 4th and 5th generation, and they're like the 12th and 14th most influential dogs in the pedigree, even though they're the only ones that appear on the pedigree that you're looking at. And then everybody else is back here in the teens and the 10s and 12s and 14s in those generations. Lastly, I want you to see Foxcliff Hickory Wind. And does anyone know of this dog? Born in 2005, it's a bitch, and her call name was?
Pedigree.
Oh God, you guys are so easy. So Hickory, and when you look at Hickory's pedigree, what we see is Fernhill's Wyvern was a sire of Electra at Fitzhugh, and we have was also the sire of Fernhill's Encore, and Lionhill Echo of Fernhill was the dam, and also the dam of Somerset, also the dam of Encore. And so the 10 generation inbreeding coefficient is 7.1. So even with the line breeding that occurred back here in the 5th generation, you still have an inbreeding coefficient of just 7.1, and you have an old generation of 18.2. So this dog is still outbred compared to your average of the population, even though she has this common ancestry. 1,000 times at 15.1. You've got Wyvern at 12.5, appearing 2 times. You've got several others, and Jewich of Springfort at 10% in the 11th generation, appearing over 1 million times. So if you look at all of them, in actuality, the background inbreeding that no one can get away from, that's behind everybody, the percentages are about the same. They may vary by 4, 5, 6%, but Tragic of Ross is always going to be somewhere between 12 and 15% because it's behind everybody. And so these are the basis and the background of your breed. And so what you're manipulating are the dogs in the close, the closer generations, but you're really not changing anything of the genetic background of your breed that has already been set. The last thing I want to point out with this is that when you look at the depth of the pedigree that you're calculating the inbreeding coefficient, if you're comparing one pedigree to another, you've got to calculate it to the same number of generations. Because as you go deeper, that inbreeding coefficient goes up, just like I showed you with the 5, the 10, and the all generations there. So, Darwin didn't have a common ancestor appear until twice until the 6th generation. It was a dog that was in the 4th, but then again didn't repeat on the opposite side till the 6th. And whereas Devil May Care in the 3rd generation already had common ancestors, and Hickory in the 4th generation. So you need to compare them at the same generational level and to be able to say this is the comparison, this dog is more tightly bred or more outbred than the other. So in order to understand about breeds, you must understand about breed evolution. The development of breeds occurred through artificial selection for body type, color, coat type, behavior, and conformational aspects. As breed lines became more specialized and stud books closed, those who did not conform to the standard were removed from breeding. Studies of dog breeds estimate they lose on average 1/3 of their genetic diversity through breed formation. And actually, I believe they lose more than 1/3. If you're looking at what they have when they first start with founders and then what they develop into 80 years later, they're losing more than 1/3. But that loss is not detrimental to the breed if it's maintaining health and increasing health and increasing quality. What you're losing is the bad stuff. And so loss of genetic diversity is not a bad thing if you are improving the quality of the breed. You want dogs to breed true. You don't want some to have good traits and some to have bad, or some to be healthy and some not to be healthy. You want them all to be healthy and all to have the good traits, which means you have to fix those traits. Fix meaning get them homozygous in those individual dogs. This is what a pedigree of a dog looks like when it goes back to founder. This is not a Scottish Deerhound. Again, with all the stuff that went on with the databases, I didn't have time to do one of these. But here's the founders of a breed. Okay, they're breeding, selecting, culling. Nope, not good, good, not good. So you have a small population where they go through multiple generations. You fix a standard, you fix a phenotype, and then you go through this population expansion where the population expands in all directions. And it actually expands further down here and further up here, but this is a pedigree of just one dog, of this dog here, his sire and dam, his grandparents, and so this picture of the breed is not the entire breed, it's only the breed that is behind that individual dog whose pedigree you're looking at. And so you get this diamond shape where his pedigree or her pedigree goes out, and you go through the expanded population, and then you get the contraction back to founders there at the building of the breed. So that's what all breed pedigrees look like when you have a complete database. So modern breed population statistics have high deep pedigree, average inbreeding coefficients, low effective population size, meaning the number of actual dogs contributed to those dogs, high average relationship coefficients to influential ancestors, and these ancestors appear in the pedigrees of every member, sometimes with breed contributions of 15 to 35%. Healthy breed gene pools require expanding or large stable populations. It allows the creation of new family lines. It allows for within breed diversity, and population contraction causes the loss of breed diversity and quality breed lines. So that's the biggest thing. Selection of breeding animals should represent the quality traits and breadth of pedigree background. Quality lines should not be abandoned. Lastly, in this section, the popular sire syndrome. So what happens with the popular sire syndrome is that a male comes along and everybody oohs and ahs and says, wow, look at him, I want to breed to him. So different bitches from different areas of the gene pool are brought to him, and they like what they produce there, and those dogs are winning, and everyone says, oh, I want to get a piece of that, and so more bitches come to him, and then you've got offspring that mature, and they start line breeding on him, and very quickly, within 1 or 2 generations, that dog's genes have been spread across the entire gene pool. And so that's what the popular sire syndrome is about. It's the overuse of a popular sire that quickly disseminates his genes throughout the gene pool without the benefit of evaluation over time. And that's the key word to a popular sire, because some people say to me, hey, what about those influential ancestors that contribute 1/3 of their genes to every dog in the population? You know, what's the difference there? Well, the difference is their ancestors competed with other dogs for breeding, and because of their quality, they continued to win out and breed and reproduce, and their offspring were of quality and were selected for use. And so each generation, you had selection that brought those dogs forward. With a popular sire, you don't have that selection. You just have them being bred, and spread very, very quickly. The insidious thing about a popular sire syndrome is that if he's found to pass on deleterious genes, then the resulting purging process also causes the loss of influence of the quality dam lines to which he was bred. So if all the bitches are going to one sire or one sire line, then and then something goes wrong and there's bad stuff there, you lose the influence of all the quality bitches from that generation. And then the last thing is that there are quality males that may not be as flashy and as fancy as that popular sire, but they may represent a different area of the gene pool, and they may have qualities that should be propagated in your gene pool and not abandoned. But because there are only so many quality bitches in each generation, they're being sidelined by that popular sire and not continuing to contribute to your gene pool. So the popular sire syndrome is the #1 cause of loss of genetic diversity in breeds. So lastly, on this point, so I'm actually going to break This is not my natural break, but it does start to talk about disorders, and so we'll break here, and then we'll get through the rest of the stuff so that we do finish by 9:30. It is right now 7:48, and I'm going to start at 8 o'clock on the dot, so you've got a 12-minute break here. Thank you. Okay, just popped to 8 o'clock. So you need to really pay attention to this slide because it goes fast. All right, so this is where I talk about diseases and disorders, which I call the dark side of breed development. Okay, one more time. The dark side of breed development. All right. All individuals carry some deleterious mutations. Everybody does. No dog is perfect. And once we learn and accept that, we can then start breeding properly without the finger pointing and without the my dog's better than your dog, and work towards improving the health of our breeds. Quality individuals who propagate will also propagate their deleterious mutations. These can cause breed-related disease if they are disseminated, and an increase in frequency through the founder's effect. So we do have to watch what we're breeding, what we're producing, and this is why influential ancestors get vetted through the generations and not all at once before you can evaluate what they're producing. Breed propagation must always include active monitoring, so health surveys, health testing, and selection. You know, what's the point of monitoring if you're not going to utilize that information in your selection to who you're going to breed to produce that next generation? It's all well and good to say, hey, I did all my health tests, but I'm breeding these two together because I planned on that before they were even born, when it has nothing to do with what I actually just tested them for. Without selection, the genetic health of the breed will decline. The genetic health of dog breeds is not a direct function of homozygosity or heterozygosity. That has to do with the size and the expansion of the population, but it is of the accumulation of specific disease liability genes. So let's talk a little bit about breed maintenance. Some registries, in response to perceived concerns with genetic diversity, propose only outbreeding to those least related and banning close matings. In Europe, they actually ban close matings. Anything closer than a first cousin or even a first cousin mating is not allowed in some European registries, so that they are saying you should only outbreed, you should never line breed or tightly line breed. However, it is selection and not the types of matings that affect breed diversity. And I can go through a whole lecture where I can show you, if you're breeding the same dogs together, but if you breed two related dogs, these two related dogs together and these two related dogs together, okay, or if you breed this one outbred to one of those and this one outbred to one of those, you're still breeding the same four dogs. You're not changing the frequency of any of the genes in the population. So outbreeding and line breeding has nothing to do with selection. It just has to do with the relationship between the dogs. And really, there are reasons to outbreed, to bring in stuff that you don't have, that you want to bring in. There are reasons to line breed, to fix something that is varying in what you're producing and you want to solidify it more. And so these are tools, they are not goals. The Mars optimal selection. So Mars has morphed many, many times in what they offer to breeders and to owners, but the optimal selection is the granddaddy of them all, that gives you the relationship between your dogs, and that they're saying you need to breed for more diversity, and that the optimal selection finds chromosomal segments that are at low frequencies in your breed compared to other chromosomal segments that are at a high frequency in your breed. And therefore, you should take the dogs that have the low frequency segments and breed them more, and breed those to increase the frequency of those chromosomal segments. They have no idea what genes are in those chromosomal segments and what they code for and what they are producing in the dogs. In all likelihood, they are minor frequency segments because of selection over many generations, that you finally got them down to a low frequency where you're not seeing those diseases or those negative traits anymore in your breed. But it doesn't matter. To a molecular geneticist, you want to breed by number. You want to change the numbers and increase those minor frequencies. It is not the way to do breeding, and it is not the way to do selection. Breed gene pool diversity requires distinct lines in order to create selective pressure. Outbreeding plans are self-limiting because as you remove the genetic differences between individuals, it becomes increasingly harder to outbreed and find mates that are genetically unlike each other. So that system, the optimal selection, the mate select system in the UK Kennel Club has come up with, what it's telling you is that the most unrelated dog to your dog is the dog that you should breed to. That is the way you should breed. Okay? But the thing is that those are the two most unrelated dogs. The offspring make those two lines related to each other. In the next generation, you now have to find a line that's unrelated to both of those lines to outbreed. And now you're related to that line as well. And then in the next generation, you need to find someone that's unrelated to all three of those lines. Otherwise, you can't outbreed anymore. Outbreeding is self-limiting. And it's not achieving any goals that have to do with quality or that have to do with health. None of the types of matings, line breeding, outbreeding, change the frequency of defective genes or their dissemination. It's selection that changes that. For dispersed breed-related deleterious genes, so if you have osteosarcoma, as an example, in a breed, I don't know which breed has that, but at any rate, you know, if you're seeing a lot of it across the breed, the genes for that are dispersed. So actually, whether the dogs that you're breeding together are more related than the average in population or less related doesn't matter. The chances of pairing up and crossing a threshold of osteosarcoma liability genes is going to be the same. So it has nothing to do with the relationship of the parents in terms of a breed-related disease. Affected individuals, if you're outbreeding, will just occur in a random fashion. If you want to know what outbreeding would do to genetic disease, look at our domestic cat populations. As a veterinarian, I see genetic disease in our cats every day. And 95% or more of our cat patients are random bred cats, our alley cats or whatever you want to call them. Okay, because only 2 or 3% less than 5% of our cats in America are purebred cats. But we see diabetes, we see inflammatory bladder disease and lower urinary tract disease, we see allergies, we see all of the genetic diseases that we see across all cats, just like we see across all dogs with allergies and our major genetic diseases, but we see them in a random fashion instead of a predictable fashion due to relationships. So my mantra is genetic diversity is breeder diversity. It's the varied opinion of breeders as to what constitutes the ideal animal and their selection of breeding stock that maintains breed diversity. If one breeder likes to line breed on one line, another breeder wants to line breed on another line, another breeder wants to outbreed, it doesn't matter. As long as everyone's doing something a little bit different, that's what maintains the diversity of a gene pool, is everyone doing their own thing. If everyone all of a sudden does the exact same thing and breeds to a popular sire or wants to do something else, then the breed will breed themselves into a corner of their gene pool, and that's what's detrimental. Everyone doing something a little bit different gives you the variety of choices of who you can then breed to in the next generation. When breeds have issues with genetic disease, the only way to improve their gene pool is through genetic testing and selection against the specific diseases and their associated liability genes. So outbreed as a panacea against genetic disease is a fallacy. And that's the same fallacy that designer breeds got their popularity from, that if you outbreed and you crossbreed, dogs will be healthy. That is not. That is false. That is a fallacy. Then there is no easy way to get health. Well, the easy way to get health is to outbreed. No, it's not. You'll still see the same diseases. The only way to improve health is to specifically select against the disease, and if you have tests, to select against liability genes. Pre-breeding health screening, this is my new mantra, pre-breeding health screening should become as universal as equine pre-purchase exams. So if you're a horse person or know about the horse, about horses, no one would buy a horse without having a pre-purchase veterinary exam to know that the horse doesn't have laminitis or doesn't have issues that or exostoses or things that are not going to allow you to ride that horse or use that horse for the purpose that you're going to be using it for. So no one is going to want to buy a horse without a pre-purchase examination by a veterinarian of their choice to tell them, yes, this horse is sound, you can go ahead and buy it. So pre-breeding health screening should become as universal. That checking the health of a prospective breeding dog is the logical and only thing to do before you decide to use that dog for breeding. So the last slide, which was what was supposed to be the first half of the talk, is that breed maintenance requires avoiding the popular sire syndrome, and these are listed in the backs of one of the articles in the handout, utilizing quality dogs from the breadth of your population to expand the gene pool, so you're expanding and increasing your population, you're monitoring genetic health through regular health surveys, you're doing genetic testing for validated breed-related disorders, you're participating in open health registries to manage genetic disorders, because many disorders don't have a genetic test, and all we can do is screen for affected versus normal, like a hip radiograph or other types of testing that you can do. And so it's only by knowing where that disease lies in your pedigrees through an open health relational pedigree database that can tell you which dogs that are close to your dogs had that disorder or not, that you can understand the risk of your dog carrying that disorder, and constant selection for health and quality. Okay, so now let's move on to developing a healthy breeding program. I would usually break for a few questions at this point, but because of our time schedule, I'm going to hold off questions till the end. And if we're a little bit over and you want to stay for questions, I'm willing to stay, but I don't want to keep people here beyond the 9:30 ending of the program. So what are your breeding goals? Your breeding goal is always to maintain and enhance the quality of the breed. And a lot of people say, Dr. Bell, you're a veterinarian, you're a geneticist. Isn't the breeding goal the best health of the breed, of breeding the healthiest possible dog? There are a lot of healthy mixed breed dogs out there. Okay, you are breeding a purebred deerhound for a purpose, and it has to be a quality deerhound. Okay, breeding healthy, ugly deerhounds does not benefit you or your breed. All right, so the breeding goal is to maintain and enhance the quality of the breed. That has to be a goal of purebred breeding. All right, and in doing so, do not limit the genetic diversity of the population. So you want to use dogs from the breadth of the population, and you want to avoid the popular sire syndrome. Then comes genetic disease control. So genetic disease control is important, but it's not the most important thing of making a quality deerhound. So with genetic disease control, our number one goal is to not produce affected individuals with genetic disease in the next generation. So your next litter you breed, you want those dogs to be clinically healthy. They may carry liability genes, but if they're going to be healthy themselves, that's the most important thing. You don't want to sell a tick and time bomb to your puppy buyers and your friends and relatives with genetic disease. So that is our goal. Are we in complete control of that? Absolutely not. But we can leverage our way to improving the situation and improving the chances of producing non-affected dogs with our matings. And then secondarily, we want to decrease the frequency of carriers of genetic disease, whether we can test for them or not, of those defective genes. Because there are some breeds that have some wacky recommendations that they have adopted as clubs. Only genetic, known simple autosomal recessive diseases in the breed, causing some significant problems, all right? Only test the males. If your males are normal, who cares if the bitches are carrier or maybe even affected? You'll never produce affected offspring. okay? And so never test your females, and that's, or at least they'll say one parent must be tested normal, the opposite parent does not have to be tested. And that's in their bylaws and code of ethics, okay? But the bottom line is if that's the way you're breeding, you're actually selecting for a 50% gene frequency for that defective gene, because carrier to normal matings produce 50% carriers. And most of the genes, defective genes across any breed, very rarely is the frequency of carriers going to be 50%. It's going to be far, far lower. So you're actually multiplying and propagating that defective gene in the population. And that's not the only gene you're going to be testing for. So then another testable gene comes along. And then a third testable gene comes along. And if you've proliferated all these carriers, you're not going to be able to find a dog that's not a carrier for this and that and that. And so you do need to decrease the frequency of carriers that are being used for breeding in the long run without losing diversity, and we'll talk about how to do that, so that it increases our choices and our ability to breed the dogs that we want to breed, that have all the qualities that we want to produce a quality dog. So let's talk about genetic tests. Let's get back to a poll. What genetic screening do you do in your dogs? What genetic screening tests do you do in your dogs? And you can respond on the website or you can text. Okay, cystinuria, so you're doing the nitroprusside testing for cystinuria. Factor 7, and echo for heart, cystinuria, factor 7. Factor 7, so factor 7, you have a gene test, okay? Cystinuria, you have a phenotypic test that measures a phenotype that is related to the disease, but not specifically for a gene that causes stones. Okay, echoes and factor 7 and basic breed identity, okay? You ask the dog, who are you? I know what you mean, but it's late. Liver shunt, okay, another one there. Factor 7, okay, so you're listing most of the major ones there that you have some screening tests for. Let's move on. So in the 2011 health survey that Dr. Dilberger had on your website has summarized for you, factor 7, the most number of you test for that. 199 people said that they tested for that. No, I'm sorry. 199 dogs were tested, and 36% of the respondents to that question said, yes, I test for factor 7. So a third of you test for factor 7. 25% of you do echoes. 23% of you run a bile acid against liver shunts. 17% of you do a nitroprusside test, but that 17% really, because that includes both males and females, that's a fudgy type of number, and we'll talk about that because there's no reason to be testing your females, and we'll talk about that as well. Eye exams, 5% of you state that you do eye exams, and 5% of you state that you do hip evaluations. So let's talk about what kind of genetic tests are available to us. There are tests of the genotype. These are direct DNA tests for liability genes. There's tests of the phenotype, which primarily identify affected individuals. So a hip X-ray or nitroprusside test or other things that, or a thyroid profile, so it tells you affected versus normal, or pedigree analysis, which is the identification of carrier risk based on the knowledge of carrier and affected relatives. We'll talk about all of these. So the panel tests that are up, let me just go through this really quick so you get the high points. So there are these panel tests now that are out, and the two major companies are Mars with their optimal selection. The optimal selection used to be the breeding tool for diversity, and now they've added in all of the genetic diseases that they can put in, and they've added in the color traits and the hair coat traits and the size traits. So all of the testable genes that they can put in are in there. And Embarq is the other company. So we'll talk about the two of those. It will report results for over 150 genetic diseases, reported in terms of known relatives to the specific breed evaluated. That's the pie in the sky answer, when in actuality they test for all sorts of stuff that has nothing to do with your breed, and they will tell you that certain genes are disease related in your breed when they actually are not. And so that's something we need to understand about. They test for more than 20 traits, including coat colors, types, and morphology. They do genetic diversity testing. Cheek swab test costs $130. And the important thing to know about these panel tests, they test for over 200,000 SNPs. And a SNP is a single nucleotide polymorphism, or a single DNA letter, an A, T, C, or G, that is different between dogs. All right, so, and they use that SNP to say, well, this is the SNP that's in the middle of a mutation for factor VII. Okay, and it segregates really well with factor VII. So we're not going to test for the whole mutation. We're just going to test for the SNP. And what that SNP tells you is that the 17,943,321st letter of your dog's genome is going to be a T if it's a normal dog, and is going to be an A if it's got the gene for factor VII. When the fact of the matter is, there are a lot of dogs that don't have the mutation for factor VII that would have an A there as a natural variation, but don't carry the mutation. So there's lots of false positives and false negatives with SNP tests, or with any of the genes being tested for in these panel tests. So if you're making a breeding decision based on a panel test, you're going to make false assumptions of whether they're carrier or normal. So if you're using this as a breeding decision, you need to run a mutation test where it tests for the actual mutation for that disease to make the proper decision. And the Embarq test, it's the same thing. They cost $199, but then you Google discounts, and you can get the $20 off discount here and there or whatever. It's still a little more expensive test, but does the same exact thing. It measures SNPs and not the mutations themselves. So it's real interesting, the reports that you can get from these things, but if you're using it for making breeding decisions, you actually need to test for the mutations within your breed. So the Canine Health Foundation is the health arm of the AKC, and so they ask the breed clubs periodically, what are the most important diseases in your breed? And they ask the health committee, and they report back, and then they collate all of the answers from every single AKC breed so that they can determine what disorders are the most important to the most breeds, and therefore where we should fund the most research. So this is why you've got cancer at the top of the list. This is why you've got hip dysplasia and other things like that, because they are breed-wide across all breeds in that regard. So before we look at their list, though, here's the one where I'm asking you about your secrets, and it is an anonymous answer. What genetic disorders are you seeing in your dogs? And I want you to be careful when you answer this. I don't want you to answer what genetic test results do you have on your dog. I'm saying, what diseases are your dogs afflicted with? Clinical disease, genetic disease. What are you seeing in your deerhounds? Cystinuria. So not cystinuria as much as cystine stones. That's the disease, is cystine stones. Cystinuria is a symptom and can be measured by a nitroprusside test. Aspiration pneumonia, heart issues, osteosarcoma. Spookiness, cystine stones. Gastric dilatation of volvulus or bloat. Osteosarcoma, factor VII, and heart issues. So someone had a dog that had clinical bleeding. It's a mild bleeding disorder, but it does and can cause bleeding, and that can occur. Heart valve disease, cardio problems. Osteosarcoma, cystine stones, osteobloat, and dilated cardiomyopathy. Okay, so you're hitting the big ones there. So here are the top 10 canine health concerns as reported to the AKC Canine Health Foundation. Number 1, hip dysplasia. Number 2, epilepsy, allergies, hemangiosarcoma as your first of the big 4 inherited cancers, hypothyroidism, lymphoma as the number 2 of the inherited cancers, gastric dilatation with volvulus or bloat, patelloluxation, cruciate ligament rupture, which is a genetic disease with a genetic predisposition. It's a traumatic precipitator, causes rupture of the ACL, but it is a genetic predisposition to having ACL rupture. Inflammatory bowel disease, cataracts, osteosarcoma is your next of your malignant cancers, atopic dermatitis or atopy, elbow dysplasia, immune-mediated hemolytic anemia, cardiomyopathy as a group, all cardiomyopathies, progressive retinal atrophy, which used to be a top 3 disease, but we found so many PRA genes and eliminated so much PRA from so many breeds that it's now a much lower issue. Mammary tumors, retained testicles, and mitral valvular disease. So those are the top 20 genetic or inherited diseases as reported to the AKC Canine Health Foundation. So let's look at some of the data from your health survey, from the 2011 health survey. So for lifespan, there were 171 females and 140 males, and the average lifespan was 8.8 years for females and 7.3 years for males. So no surprise that the females outlive the males a little bit. We've known that in your breed in the past. Minimum of 0.8 years to 16 in females and 0.3 to 13.6 in years. But the best way to do an analysis of lifespan is to look at a cohort where you follow every dog until they pass away. And therefore, you then know what the age is, the average age or average lifespan of that entire cohort. Looking at a health survey and saying, did your dog die? What age did it die? Doesn't really look at a cohort. So those numbers sometimes are not exactly what we think that it's telling us. But in general, it is telling us the average. So when you do a complete lifespan analysis, females were 9.8 years and males were 8.3. So just a little bit older and a little bit longer than it was answered in the health survey. Cause of death. So this is dogs that died with a definitive diagnosis, at least a definitive enough for you to fill out a health survey form, not with veterinary verification, but we figure for most of these, your vet told you what it is, and so this is what we had. Osteosarcoma is the highest at 21.5%. Average age in years, and I'm taking 7.4 to 8.5 only because Dr. Dilberger broke it out by sexes, and so I just used the 2 sex numbers as your average and put a line between them. Cardiomyopathy, heart failure from cardiomyopathy as the cause of death, 12.4%. Old age hind end issues, 6.2%. And I want you to remember that. Okay, if your dogs are having age-related hind end issues, that's due to arthritis. Okay, that is due to pain and discomfort, and then you get muscle atrophy, and that is something that you're dealing with there. And dogs will vary at how much hind end arthritis they get based on the quality of their joints, as well as osteoarthritis is a heritable disease. Different dogs will develop arthritis based on the genes that they have. And the food companies discovered this well over 20 years ago, where they figured out that there was genes that could be upregulated and downregulated that controlled arthritis, and they made foods to downregulate those inflammatory genes that precipitate towards arthritis in the development of their foods. So they were the first ones that identified osteoarthritis liability genes. Heart failure due to unknown, stomach torsion or bloat at 4.4%, old age without hind issues, pneumonia, accident or injury, liver shunt, lymphoma or lymphocytic leukemia, spondylitis or spondylosis, metastatic cancer, arrhythmia at 1.8, bleeding after surgery 1.8, hemangiosarcoma 1.5, and degenerative myelopathy 1.5. And here's where I need to point something out to you, because we will talk about this a little bit later before we finish. Degenerative myelopathy as a disease process does not exist in your breed. Does not exist in your breed. No Scottish Deerhound has ever been histopathologically diagnosed with degenerative myelopathy by the experts that work on this disease. And there are pathologists that get fooled because there are a lot of degenerative spinal cord conditions, both acquired and inherited, that can look like degenerative myelopathy, but you need to look at very specific tracts in the spinal cord in very specific locations in the lumbar vertebrae because those tracts change as they travel through and to diagnose that disease. And there are many, many mimics. And if you actually read the scientific articles written by the groups from Missouri that has done all of this work at the medical and the veterinary school, they talk about all the mimics. And they talk about all of the things that they see that end up not being degenerative myelopathy. So just because a dog is weak and sinking in its hind end does not mean it has degenerative myelopathy. And there are actually only 6 breeds that have clinical degenerative myelopathy as a significant issue in their breed where they need to be testing for that. And we'll talk about that later on. In the UK Health Survey of 2014, it listed the cause of death as cardiac failure, cardiomyopathy, bone tumor, aggression, arthritis, cancer, cardiac tumor, bloat, kidney failure, old age combinations, and splenic tumor. They gave no numbers on their survey, but those are the most common causes of death. In your health survey question of what genetic disease does your dog have, osteosarcoma, 10.4% was the highest. Cardiomyopathy, 9.1%. Deerhound neck, 6.5%. And you guys know what Deerhound neck is, even though the scientists still don't know what it is. Okay? I mean, there's a question. Is it a proliferation of bone like a wobbler syndrome? Is it a sterile inflammation of the arteries around the spinal cord, a sterile meningitis arteritis like we see in beagles and other breeds? Is it a combination of those? Is it partly disc disease? The questions are many, the answers are few, but we do know approximately what age, around 3-4 years of age in male dogs, and younger in female dogs a little bit. And most dogs with medical therapy completely recover and they're fine. So that is a disease that you do see in your breed. It's obviously has inherited features, so we should select, we should identify dogs that have that. Is it the most important disease of your breed? No. If it's self-limiting and curable, it's a heck of a lot better than osteosarcoma, isn't it? All right, so you select against it, but it has to be prioritized in terms of how severe it is, but it doesn't mean that you ignore it in that regard. Allergic dermatitis, heart failure, bloat, arrhythmia, pneumonia, cystinuria or stones, and that's 4.4% of males only. Seizures, retained testicles, and that's 3.3% of males only as compared to males and females for the other things on this list. And then splenic torsion at 1.9. That's 588 dogs in the health survey. So let's talk about some of these diseases really quick. And I am going to go a little bit fast because most of this stuff is in on your website and in the materials from the health committee. Primarily leg bones in the large and giant breeds, 5% incidence in your older health survey at 8 years of age average. That was in the health survey prior to 2011. Researchers report up to 10% incidence in Scottish Deerhounds, no known mode of inheritance, and you want to use breeding management for unknown mode of inheritance. That's what we do. We know it's complexly inherited, multiple genes involved, and so when I talk at the end about how you select against certain things, if you have an unknown mode of inheritance, it's the same selection that you would do for a complexly inherited disease. So Dr. Carlos Alvarez has funded research in your breed on osteosarcoma. He is an MD physician at Nationwide Children's Hospital in Columbus, Ohio, and he published a study in March of this year, so 2 months ago, on osteosarcoma in greyhounds, Irish wolfhounds, and Rottweilers. So those are 3 breeds that he had enough samples to work with and look at the results. And his research was actually based on the research that was published from the Bloat Institute in an article by Eleanor Carlson, or first author Eleanor Carlson, but for the whole group at the Bloat Institute in Boston, that reported on many genes, I think 40-something genes that could be related to osteosarcoma. And he applied some additional tools that he used to limit it down to just 13 genes that he felt were important in osteosarcoma. They're positively correlated, although there are differences between the breeds, which genes were more influential in which breeds, which genes tend to travel together, which genes didn't. So we have some answers. Nothing is testable at this point. We don't have a complete answer as to what causes osteosarcoma or what actually is a standalone genetic risk factor for osteosarcoma and should be selected against. So this is all the stuff that still needs to be done. And each generation that we deal with in molecular genetic research, we go through these paradigm shifts where all of a sudden we start to understand something we didn't understand before. And that's where we are with complexly inherited disease. How do you deal with a genetic disease that can be caused by multiple genes, that each of those multiple genes does not have to have an equal contribution in every single dog? Sometimes some genes have more of a contribution in one dog, and sometimes others have more of a contribution. There's environmental variation, there could be diet variation, there could be all sorts of things. And how do we make a picture that can explain it in a way that's practical to us to use that information for breeding? That's the paradigm we haven't crossed yet with any complexly inherited disease, but that we are working on. So we need further studies there. Scottish Deerhound cardiomyopathy, dilated cardiomyopathy, similar to that seen in other giant breeds. Survey incidence of 5 to 8% in the old survey. The new survey has had the figures I already went through. Causes abnormal heartbeats or heart failure, sudden death, passing out, exercise intolerance, pulmonary edema due to heart failure, causes heart failure of both ventricles and atrial fibrillation, where the atria are fibrillating. Average age of clinical signs is 6.5 years of age. Use control measures for polygenic diseases. I spoke to Dr. Kate Muirs at NC State. She performed whole genome sequences on a few affected Scottish Deerhounds. Now, whole genome sequencing is what they first did to sequence the genome of man. And then in dogs, Tasha was the first dog that was done. It cost millions and millions of dollars in man. It costs hundreds of thousands of dollars to sequence Tasha. We can now sequence an entire genome at this point for $750 to $800, sometimes even $500 at some places. So the price tag has come down significantly, where a whole genome sequence means the entire letter of every single gene on every chromosome for that individual dog. So not just spot checking one gene here or one gene there. So she did whole genome sequence to look for a gene of major effect, a Mendelian gene that has, even though it's not a simple Mendelian disease, is there one major gene that seems to be highly influential in the Scottish Deerhound? And the answer was no. And so there's no further research being done by Dr. Muirs or anyone at this point in time with cardiomyopathy. And it's probably a good thing, because we're not at the stage yet where we can figure out how to utilize the genetic information from complexly inherited disease in a breeding manner. So she has found a gene in Great Danes that seems to be X-linked. She has found a gene in boxers. She has found 2 genes in Doberman pinschers. And whether those are the whole story or can be selected on by themselves to actually increase or decrease the frequency of cardiomyopathy in those breeds has not yet been determined. We know that those genes are involved in the story, but to start selecting and neutering or breeding based on those genes today is not the whole answer and could even be detrimental to what you're trying to do to improve your breed. So the fact that you don't have something to select on right now, except for who's affected and who's not affected, is probably a good thing until we come up with better answers. Heart statistics from the OFA website: 147 deerhounds were evaluated, 94.6 normal, 3.4% equivocal, which was 5 dogs, and 2% abnormal, which was 3 dogs. Now the heart database for the OFA is a elective database, and you already know what your answer is when the cardiologist hands you the certificate before you decide whether you send that into OFA or not. So there's a lot of pre-screening, and so we tend not to have the listings of the affected dogs in the database, and so you see a lot of normals. But even with that, there are abnormals being reported. Bloat, and this is the same information I told you from Dr. Glickman's work in the 1990s. Each year over 3 years of age increases the risk of bloat by 20%. An affected first-degree relative increases the risk of bloat by 2/3. Eating quickly increases the risk of bloat by 15%. And raising food and water bowls increases the risk by 110%. And that was a very controversial finding when he first came out with it. And Dr. Glickman is one of those really, when you're an epidemiologist, the word is not anal, okay? When you're an epidemiologist, the word is that you are exact and you will not accept anything less than exactness in the data. So when he did his study, any person enrolled in the study that knew of a relative of their dog that had bloat was excluded from the study. It had to be a completely naive population so that the people raising their food bowls or lowering their food bowls were based on what they wanted to do and not based on known risk that was already in their pedigrees. And he found that it increased risk. Now, does it really increase risk or not? And there's all this stuff about swallowing and gulping air and all that kind of stuff. The bottom line was raising the food bowls did not lower the risk. We can definitively say that. Whether raising them or not increases the risk can be debated, but if you're raising your food bowls because you think you're going to decrease the risk of bloat, it wasn't happening. And that is something definitive. Increased chest to depth width ratio measurements, so that the ratio of the depth of the chest over the width of the chest, as that increased, the risk for bloat increased. Solely feeding a dry dog food, feeding a single large daily meal, leanness, fearfulness, nervous or aggressive temperament, those were all risk factors. And if you think about bloat, because I have Gordon's, which is a bloat risk breed as well, and you think about what happens with bloat and which breeds have bloat. First of all, it's the deep-chested breeds. And what happens in a deep-chested breed? There's a lot more room for the organs to move around in. So the stomach hangs in the abdomen behind the chest there, and it's attached to the liver above it by what's called the gastrohepatic ligament, gastrostomach hepatic liver ligament, and it hangs there. And if you have a very deep chest, that stomach can stretch that ligament. That ligament needs to stretch in order for that stomach to twist, okay? Feeding a single large daily meal puts a heavy load on that stomach, where you have a very deep-chested breed where that stomach has a place to go. You go to these flat-chested breeds, there's no place for that stomach to go. It's resting on the rib cage. So in a deep-chested breed, that single large meal can stretch that gastrohepatic ligament, give it enough room. Fearful, nervous, or aggressive temperament. Fearful dogs, are they fat or skinny? They're skinny mostly. Okay, they're not all skinny, but they're burning off a lot of nervous energy if you're talking about these really nervous dogs, okay? And that's what he was documenting in his survey. So these dogs don't have a lot of abdominal fat to act like packing peanuts to hold that stomach in there. There's a lot of empty room for that stomach to be swinging around on that ligament, stretching it out, and flipping over. And so these were the factors that he found in his study. And use a control for a complexly inherited disease. Cystinuria. So let's compare the Newfies from the Deerhounds. Newfies have an early onset where the stones form prior to 6 months of age. Deerhounds late onset, stones form at 3 to 4 years of age. Newfies, affected dogs uniformly have high levels of nitroprusside. Deerhounds, intermittent high or low levels on the nitroprusside test. But what we now are finding out is that I'll get to it in a second, okay? Let's do this in a stepwise fashion. Newfies, equal ratios, males and females, though only males block with stones. So females are testing with a nitroprusside test, but they don't form stones. In deerhounds, females do not test positive on the nitroprusside test. Are there levels of purines and proteins that can give you a false positive? Yes, but they can actually analyze what those are and find out what other proteins that aren't cysteine that are causing a false positive nitroprusside. But cysteine as the protein that is looking at with the nitroprusside test does not accumulate in the females. And there's no direct test yet in the deerhounds. We do have a direct gene test in the Newfies. So the bottom line of what Dr. Henthorn, and this has been the disease of her life. This is a disease she started with very early in her career and has been working on her entire career in many, many different breeds. And the same situation that occurs in deerhounds is occurring in many other breeds. And so it is being documented again and again exactly what the parameters of cystinuria are. Intact male deerhounds can test positive on a nitroprusside test. Neutered males and females will never test positive for cysteine on a nitroprusside test. And that is what the bottom line is of nitroprusside testing. And we didn't know about this early on. And so, why were neutered males not testing positive? Or why did a male that formed cysteine stones and was neutered at the time of his stone removal, okay, and then finally he got nitroprusside tested and he was negative, but he formed stones? Well, he was tested after he was neutered, okay, and once you're neutered, it is sex hormone related, and they still don't know exactly what that relationship is and why that causes the stones and why that causes the positive test and the production of cysteine, but that's what we do know now, is that you should only be testing your intact males. That's the only ones where that nitroprusside test gives you reliable and valid results. Not females, not neutered males. So if you want to test for liability to producing stones, because not every dog that has a positive nitroprusside test will form stones during their lifetime, but the only ones that will are the ones that have a positive test. So if you're using dogs for breeding, or you're making decisions whether you breed a dog or you don't breed a dog, or you already bred a dog and then now you're deciding to neuter him, if you've never done a nitroprusside test, you should do it before you neuter them so you know whether there's risk there of possibly passing on genes for forming cysteine stones. In the 2011 health survey, 58 males were tested. I'm only looking at the males now because I don't want to confuse the story with the 34 females that all tested negative that we expect to test negative. 27 tested positive to the nitroprusside test. 2 of them had no stones. 11 had stones, 1 not reported. For the ones that tested negative, 73% tested negative. 38 had no stones, 3 did have stones, but when Dr. Henthorn goes back and queries about it, those dogs were neutered prior to their tests, and 3 not reported. So that's the story that we know of now on cystinuria. Are there going to be some weird outliers in many or any disease? Yes, there are, okay? And sometimes we'll come up with the explanation for it, sometimes we won't. But this is the story of cystinuria, and this is what you need to understand and follow, because that is what happens in 99.9% of the cases. Congenital liver shunts, an abnormal vessel that bypasses filtering by the liver, allowing ammonia and waste products to circulate in the bloodstream. The symptoms, slow stunted growth, signs of hepatic encephalopathy because the waste products that are supposed to be removed by the liver are now hitting the brain and causing confusion and abnormal mentation, drooling, seizures, mental confusion, especially after a high-protein meal. Because this is where the blood ammonia and the waste products the high nitrogen waste products would occur with beef and liver and high protein meals. It's diagnosed by measuring blood ammonia or blood bile acid levels. The bile acids is a more sensitive test, but it also has a lot of false positives and negatives depending on whether the dog got spooked and its gallbladder contracted right before you took that sample. Because the gallbladder contracts, it dumps bile acids into the bloodstream, and you're going to see high levels there. You confirm a shunt by ultrasound or a surgical contrast X-ray study. Our ultrasound machines now are so good that you can do it by ultrasound. Also, in a Deerhound, it's much easier to see a shunt than it is in a Cairn Terrier. In the Dutch study of Deerhounds, they showed a 5% incidence. We don't know the exact incidence in your breed. It's a low incidence, but it does exist. The mode of inheritance is unknown. Use control for unknown or polygenic inheritance. Bile acid test statistics for Scottish Deerhounds on the OFA website, 42 evaluations, all normal. And I understand that you guys are not used to sending in results to the OFA, but hopefully when I go through the reasons that it's helpful if you do report results of your genetic screening, you'll understand how it represents your breed and how it actually helps you as breeders.